Hello, everyone. We learned the concept of sequence. We know that sequence is a special function. By analogy with functions, we summarized the concept of sequence from some facts according to the following path and studied the representation and related properties of sequence. In the study of function, after understanding the general concept of function and the research content of function properties, such as monotonicity and parity, we not only deepened our understanding of function, but also mastered the very useful function models such as exponential function, logarithmic function, and trigonometric function by studying some special functions such as basic elementary function. Similarly, after understanding the general concept of sequence, we should study some sequence with special change rules, establish their general term formula and the first n-term formula, and use them to solve practical and mathematical problems. Today, we will study a kind of basic special arithmetic sequence. What is an arithmetic sequence? Let's start with a few examples. Please look at the sequence of the following questions. Can you find their rules? The first sequence is the ground slate tree of the round mound altar of the Temple of Heaven in Beijing. The ground of the circle altar of the Temple of Heaven is paved with stone slabs. The center stone is round in the middle, and around the center stone is a 9-circle fan ring stone slab. The number of stone slabs in each circle from inside to outside is 9, 18, 27, up to 81. The second sequence is the corresponding size of a certain type of garment top. The corresponding sizes of different types of clothing tops are 38, 41 to 48 respectively. The third sequence is to measure the atmospheric temperature below 500 meters in the vertical direction of the ground. From 20 meters above the ground, the atmospheric temperature at every 100 meters of increase is 25, 24, and up to 21. Let's take sequence 1 as an example. The second item of sequence 1 is 18, equal to its first term 9 plus 9. The third term 27 is equal to its second term 18 plus 9, until the last term 81 is still equal to its previous term 72 plus 9. In other words, the second item 18 minus the first item 9 equals 9, the third item 27 minus the second item 18 equals 9, until the last item 81 minus its previous item 72 equals 9. If a n is used to represent sequence 1, a 2 minus a 1 equals 9. A 3 minus a 2 equals 9, and a 9 minus a 8 equals 9 until the end. It is not difficult to see that as a sequence 1, there is such a rule that from the second term, the difference between each term and the previous term is equal to the same constant. Let's see if sequence 2 and sequence 3 have similar laws. For sequence 2, we find that from the second term, the difference between each term and its previous term is the same number 2. For sequence 3, from the second term, the difference between each term and its previous term is the same constant -1. Therefore, sequence 2 and sequence 3 also have similar laws. The sequence in the three examples just now is an arithmetic sequence. Then can you give the definition of arithmetic sequence from the example just now? We say that if a sequence starts from the second term and the difference between each term and its previous term is equal to the same constant, then this sequence is called an arithmetic sequence. This constant is called the tolerance of the arithmetic sequence and is usually represented by the letter D. Please note that in the description of the definition, there is no previous item in the first item since the second item. The difference between each term and the previous term indicates the order of doing the difference, and the same constant is the origin of the name of the arithmetic sequence. Please understand the preciousness of definition narration. Can you judge whether the following sequences are arithmetic sequences according to the definition of arithmetic sequences? The first sequence is 5, 9, 13, 17, 21. We find that from the second term, the difference between each term and the previous term is 4, so it is an arithmetic sequence with a tolerance of 4. Look at the second sequence. 9, 7, 5, 3, 1, -1. The same is true for this series. From the second term, the difference between each term and its previous term is the same constant -2. So it is an arithmetic sequence with a tolerance of -2. The third sequence is a constant column where each term is 6. According to the definition, starting from the second term, the difference between each term and the previous term is a constant of 0, so this constant column is still an arithmetic sequence with a tolerance of 0. The fourth sequence is a n alternating sequence of 0 and 1. It is not difficult to observe that the second term 1 minus the first term 0 equals 1, while the third term 0 minus the second term 1 equals -1. Obviously, they are not equal, so the fourth sequence is not an arithmetic sequence. We know the definition of arithmetic sequence. Please consider, how many terms do an arithmetic sequence need at least? It should be 3 items. So please think, if you insert a number a between two numbers a and b, making these 3 numbers an arithmetic sequence, what conditions should the inserted number a satisfy? It is not difficult to find according to the definition. The difference between the second term a and the first term a should be equal to the difference between the third term b and the second term a. Therefore, we have twice the value of a, which is equal to a plus b, that is, a equals a plus b divided by 2. At this point, we refer to as the arithmetic mean of a and b. That is to say, in the arithmetic mean of the arithmetic difference between two numbers a and b. This property is of great significance in the study of arithmetic sequences. With the concept of arithmetic sequences, we naturally wonder, what is the general formula for them? How to derive the general formula for arithmetic sequences? Through the previous lesson, we learned that in addition to the general term formula, the recursive formula is also a representation method for sequences. It has a close relationship with the general formula. So, can you write a recursive formula for arithmetic sequences based on the definition? We assume that the first term of the arithmetic sequence n is a 1 with a tolerance of d. According to the definition, starting from the second term, the difference between each term and its preceding term is equal to the same constant, which can be expressed in symbolic language as n plus 1 minus n equals d. This equation is both a symbolic language representation of the definition of arithmetic sequences and a recursive formula for arithmetic sequences. From the recursive formula, we can sequentially write equations where the difference between each term and the previous term is represented by the same constant, starting from the second term. That is, a 2 minus a 1 equals d, a 3 minus a 2 equals d, a 4 minus a 3 equals d, and so on. Let's rephrase it as a 2 equals a 1 plus d. A 3 is equal to a 2 plus d. Then, by substituting the previous conclusion into the organization, we obtain that a 3 is equal to a 1 plus 2 times d, and similarly, a 4 is equal to a 3 plus d. By substituting the previous result into the organization, we obtain that a 4 is equal to a 1 plus 3 times d, and so on. It is not difficult to observe such a general pattern. A n is equal to a 1 plus n minus 1 times d. Please consider whether this equation holds for all positive integers. We noticed that the recursive equation just now starts from a 2 being equal to a 1 plus d. So this equation currently only holds for positive integers greater than or equal to 2. What should we do when n equals 1? As you can imagine, we can substitute n and 1 for verification. When n is equal to 1, the above equation becomes a 1 equal to a 1 plus 1 minus 1 times d, which is also equal to a 1. This indicates that the equation we just summarized holds for all positive integers. According to the recursive formula of arithmetic sequences, first write some specific recursive relationships, observe their patterns, and summarize to obtain a general conclusion. This reasoning approach, which goes from special to general, is also an important method for discovering new laws and conclusions in mathematics. However, the conclusion drawn from inductive reasoning is a conjecture and not reliable. Think about it, can we use other methods to derive the general formula for arithmetic sequences? We can still focus on the recursive formula, because we require a n. This time we will start from n and write out the recursive equations from a n to a 1. That is, subtracting a n and subtracting 1 from a n equals b, subtracting 1 from a n and subtracting 2 from a n equals b, and so on. I kept writing until a 2 minus a 1 equals b. How many equations have I written in total? It should be n minus 1. We can discover patterns from the subscripts of the subtracted or subtracted terms. This is also a common method for counting the number of items in a sequence. Now let's add up the equation of n minus 1. We have discovered the subtraction term of the first equation and the subtracted term of the second equation have been eliminated. The subtraction term of the second equation and the subtracted term of the third equation have also been eliminated. The subtracted term of each subsequent equation and the subtracted term of the next equation are eliminated. So after the final accumulation, there is only a n and negative a 1 left on the left side of the equation. The right side of the equation is all d, so there are n-1 equation in total. So we get that subtracting a 1 from a n equals subtracting n by 1 times d. We move a 1 to the right side of the equation, and we get d, which is equal to a 1 plus n-1. This is completely consistent with the general formula we obtained using inductive methods just now. But this time we started from the recursive formula and derived the general term formula for arithmetic sequences using the cumulative method, which is a rigorous derivation method. This method has a very wide range of applications when deriving general term formulas from recursive formulas such as arithmetic sequences. From the general formula, we can see that knowing the first term a1 and the tolerance d, we can obtain any term in the sequence n. Next, let's take a look at the three arithmetic sequences we just encountered. Can you write the general formula for arithmetic sequences? The first terms of these three sequences are 5, 9, and 6, and we have just studied that their tolerances are 4, -2, and 0, respectively. So according to the general term formula, we can obtain the general term formulas for these three sequences as for n plus 1, -2 n plus 11, and 0, respectively. We know that a sequence is a special function. Specifically, from a functional perspective, please observe the general formula for arithmetic sequences. Which type of function is it related to? We can write the general term formula in the form of a function about n, which is d times n plus a 1 minus d. It can be seen that when d equals 0, a n equals a 1, which is a regular function. When d is not equal to 0, a n is a linear function fx equal to dx plus a 1 minus d. When x is equal to n, the function value is a n equal to fn. So, since an arithmetic sequence with non-zero tolerance can be regarded as a linear function, what is the relationship between the image of arithmetic sequence n and its corresponding linear function fx, where fx equals dx plus a 1 minus d? We can create a n image of the sequence n in a Cartesian coordinate system. From the content of the previous class, we know that there should be some isolated points, and its corresponding linear function graph should be a straight line passing through these points, with a slope of tolerance d and a n-intercept of a 1 minus d. These points are evenly distributed on this line. So, conversely, if the linear function fx equals kx plus b, where kb is a constant, the resulting sequence n equals kn plus b, is it necessarily an arithmetic sequence? To determine whether a sequence is an arithmetic sequence, we need to define it. Since we already know n, we can write expressions for a 1, n, and a n plus 1 ... So we can get a n plus 1 minus n, and substitute the result into the constant k. That is to say, the sequence n is an arithmetic sequence with k plus b as the first term and k as the tolerance. In fact, the sequence n is an arithmetic difference with a non-zero tolerance, and the necessary and sufficient condition for the sequence is that its general term formula n is a linear function of n. Since the arithmetic sequence can be seen as a special linear function, we think. Can we study the monotonicity of arithmetic sequences from the perspective of functions? The monotonicity of a linear function depends on the sign of the coefficient of the linear term, and as a linear function, the coefficient of the linear term of the arithmetic sequence is precisely the tolerance d. Therefore, it is not difficult to see that when d is greater than 0, the sequence n monotonically increases, while when d is less than 0, the sequence n monotonically decreases. Specifically, when d is equal to 0, the arithmetic sequence n is the constant sequence we just saw. This is also consistent with the conclusion we obtained through the example just now. Okay, after studying the general formula for the concept of arithmetic difference, let's take a look next. What problems can be solved using the general formula for arithmetic sequences? Please refer to example 1. The general formula for the arithmetic sequence n is that n equals 5 minus 2n. Find the first term a1 and tolerance d of the arithmetic sequence n. This problem should not be difficult for everyone because the general formula is known. We can calculate a1 by substituting n into the general formula, and by using the general formula to write n-1, we can calculate the tolerance d by subtracting a n-1 from a n. To organize the previous idea into a solution process, which is to substitute n into the general term formula and obtain that a1 equals 3. When n is greater than or equal to 2, we obtain the expression for subtracting 1 from a n by subtracting 2n from 7. Subtracting 2n from a n by 7 results in a constant -2. So the sequence n is an arithmetic sequence with a first term of 3 and a tolerance of -2. Please think about it. Are there any other methods to obtain the tolerance d? Do we need to subtract n and n to obtain the tolerance? Someone must have already thought that since it is known that the sequence n is an arithmetic sequence, the difference between each term in the sequence and its predecessor is equal to the tolerance d. Since we have already calculated the first term a 1, we only need to calculate a 2 again, and subtracting a 1 from a 2 is the tolerance d. So we can get a faster solution to this problem, which is to find that a 2 equals 1, and a 2 minus a 1 is the tolerance -2. Can you please reconsider and directly determine the value of tolerance force from the general formula? Since we have just analyzed that the formula for the general term of an arithmetic sequence is related to n, and the coefficient of a linear function is exactly the difference d, we can directly see the value of the tolerance d from the general term formula. This is the solution 3 we obtained based on the analysis just now. In fact, once we know the formula for arithmetic sequence terms, we can directly read the value of tolerance d from the coefficient of n. Through the answer just now, we know that when studying sequences, we can use the perspective of functions to treat the general term formula or the sum of the first n terms of the sequence as a function of n, and use functional methods to obtain the relevant properties of the sequence. This is a common method we use when studying sequences. Looking at example 2 again, find the general formula n and the 20th term for arithmetic sequences 8, 5, and 2, and determine whether -289 is a term in the sequence. If so, which item is it? We know that as long as we obtain the first term a 1 and the tolerance d, we can obtain the formula for adding terms to the sequence, thereby obtaining the 20th term, and the tolerance d can be obtained by the difference between any term and its predecessor. For the second question, after obtaining the general term formula, we can consider it as an equation about n. To determine whether -289 is a term in the sequence, we only need to see if -289 can give the equation a positive integer solution. The process of organizing the analysis just now into a solution is as follows. Calculate the difference between the second and first terms to obtain a tolerance d equal to -3. Substitute the first term to obtain the general formula, where a n equals -3n plus 11, so a 20 is equal to -49. Let's make -3n plus 11 equal to -289, so n equals 100. So the -289 is the 100th term in the sequence. From the previous answer, we know that the first term a 1 and tolerance d of an arithmetic sequence are the fundamental quantities of the arithmetic sequence. From these two fundamental quantities, the formula for the general term of an arithmetic sequence and any term in the sequence can be obtained. The common method for solving problems related to arithmetic sequences is to list equations or systems of equations about unknown variables in the general formula based on known conditions, and obtain the unknown variables. Finally, let's review the exploration process of this lesson. What have you learned? From a knowledge perspective, we have studied the definitions of arithmetic sequences and arithmetic terms, derived the general term formula, and applied it briefly. In this process, we have the definition of arithmetic sequences and write the recursive formula for arithmetic sequences. Derive the general term formula for arithmetic sequences using both inductive and cumulative methods based on recursive formulas. We have understood and recognized the general term formula from the perspectives of functions and equations, and solved some simple problems. From the perspective of research methods, we write recursive formulas based on definitions, and then derive general formulas using appropriate methods. This is a common method we use to study special sequences. We will continue to use it when studying arithmetic sequences in the future. After obtaining the general term formula for arithmetic sequences, we applied the general term formula from the perspectives of functions and equations to solve some simple problems. The ideas of functions and equations play an important role in our learning of sequences, and we hope that everyone will continue to appreciate their application in future studies. That's all for this class. Goodbye, everyone.